Well, I want to talk about a real case that I've experienced with a malware campaign. So different clients received the same attack, the same entry vector, and we started looking for something that could be related to that attack so that we could act in advance. So, well, the name is Evolution of a Malware Campaign, a real case. So first of all, I want to introduce myself. My name is Yassin Said I'm part of the Palma Valencia analysis group, and I'm also in charge of doing research in this field. Here you can also see my LinkedIn and Telegram, etc., in case you want to ask me any question at some point. So what am I going to explain in my presentation? We are going to have a small presentation regarding how malware started attacking the clients, the main characteristics. Well, especially we are going to see what the malware started doing. And then we will see 5 cases in which the attack has been improved by the attackers. Then we are going to compare what has happened since then throughout the campaign. Then we are going to identify the campaign and the main actors. And finally, I'm going to show commitment identification table and some links of interest in case you want to know more about this. So regarding the introduction, what was the situation? Well, a new campaign arrived. Systems could stop that campaign, but many samples of this campaign were starting to arrive, and we had to do something. Why? Because malware changes. So the issue here is that even though a tool can stop an attack, can prevent an attack, the attack is going to become more sophisticated. The entry vectors are going to change, and at some point they may be harmful for me. So we started our research in order to see how the campaign was working. We did reverse engineering for that. And we tried to find as much information as possible in order for our system to respond in an appropriate way. So what was I doing? I was looking for commitment identifiers, entry vectors, URLs, strings, hashes from the malware or the executable file, packers. Why? Because I wanted to identify that sample. I wanted to be able to know that everything that is arriving and that's linked to that sample is kept by me, and I can get more strings from that in order to strengthen my security systems and to act in a more proactive way instead of reactive way. So, in initial background, if our clients were receiving an email with a phishing, so it was an email that faked some real content and had some Office document with macros. These macros were containing malicious content. The user, as he or she is in a hurry, allowed the execution of this malicious content. This is one of the documents I could obtain from the campaign, and this is a document that fakes a legitimized content. The document is asking us to enable the macros in order to execute the malicious content. I extracted the macros, all this code that you can see here, and I went to my laboratory equipment and I checked if this was doing what it was supposed to do. So what is this sample doing? Well, it started creating files in temporary files, different types of files such as DLLs. And what is it doing with the DLL? It uploaded the DLL, and that's the end of the execution. So if I create directories and the only thing that I have is a DLL, which is something that is going to execute, here is my starting point for my research. So after doing our first static and basic analysis, we could see that we have the text section which corresponds to an executable file, then we see that it's just less than 12%, but the data section is 83%. Data section is going to have the variable, the global variables. This is quite weird. It is very weird that this doesn't have any code. In the part of imports, we can see that we have almost no functions, some memory content, it may be something or not, and the export section is completely empty. Why is this important? A DLL is the abstraction that Microsoft has in order to create coding libraries. This is how they do this type of library. So if I have a DLL and I don't have any export to invoke, this means that the coding is somewhere else. So the functionality of this that this should have, it doesn't have it. So let's see more the sample more into depth. So if it doesn't have the codes, the exports, and the imports, where is the code, the malicious code, going to be? In the DLL main. Maybe some of you already know this, but this is the part of the code that is in charge of setting the environment in order to charge potentially some of the exports. This is what I saw when I inspected the LLM main. So here we can see a lot of code. We can see that the file is trying to fake a legitimate string by pretending to be a type of software, and this here is a malicious code. What do we have in this malicious code? We are going to have the reference to the obfuscation and the packing. We're going to see how this obfuscates the content and starts injecting. So first, we are going to see this obfuscation. We are going to see that it's going to do a memory, it's going to obtain some memory space, it's going to decompress the code, and it's going to put it in a loop that's going to be in charge of filling the memory with a vector that's inside the data sector that's going to start this obfuscating when we apply that code and we shift to the bit. And then we're going to have another XOR operation. So once the memory is disobfuscated, what's the next step? We should know if the thing that we're having here is code or not. As we can see here in this call, this is calling virtually to the memory section that has filled. This means that we're going to have a code. The result of doing an operation such as this one is translated into a redirection of the operation flow. So we've seen the obfuscation. Now let's see how we can unpack this sample. If with the debugger I go to the memory section that I've been linked to, what I'm going to see is this lot of strings that have been hardcoded and that are now part of the pile. And this is translated in all these so-called library methods that are going to help us to get some conclusions. So this malware is going to host some memory in order to do more decompression through an MSET. The decompression process is going to take place before and after changing the parameters of the hosted memory. The memory, which is interesting, is the one that's going to change permits. So for me to execute a memory area, I'm going to have to provide with permits. And this is what I'm going to do with virtual protect. This is how I'm going to be able to execute that memory. What would be logical in this case would be establishing different points in order to learn the memory addresses and also the virtual, I'm going to work in the virtual and in the virtual project. And once I'm working in the virtual project, I know that after doing all the coding, the injection part is going to be remaining. So when I watched with virtual protect what was inside, we could identify the BP strings, and we could see this program cannot be running in those modes. So this sample is already unpacked. So now we have to keep it and to continue with our analysis. So we've seen that the obfuscation, the repackaging, but how is the injection going to happen? Well, we're going to have the reflective technique, reflected delete injection. This is like the initial diagram. Let's imagine that we have an attack and a victim. The victim process is going to have a malicious DLL already downloaded, and our attacker is going to be able to access that memory area. And it's going to call the reflective loader. The reflective loader is going to be invoked through this EAT, this export. It's going to upload the DLL, it's going to execute all the malicious content, and it's going to end the execution of the DLL with that reflective loader. Is going to go back to the normal execution flow. Into detail, we can see that the reflective loader, through remote thread or shell code, is going to calculate its own image base, and this is the reference that it's going to use. When the attacker wrote in the memory the DLL in the victim, it did it in a random address, so it needs to be stored in the memory in order to start parsing libraries such as virtual alloc, to gain some memory, to get extra memory space in order to inject the DLL, and to start loading and injecting the headers, the sections, the IAT, the relogs, etc. Once we have that, the reflective loader is going to call the entry point of the DLL, and the DLL starts being executed. So the malicious DLL is executed, and after the execution, the reflective loader returns the flow to the normal program flow. Let's see an analysis of the unpacked sample. We have the obfuscation, unpacking, and injection. Now let's see what this is doing, what the malware is doing. I'm going to be able to analyze that right now. So in summary, we're going to see that there are connections with the CNC. We're going to see how this is sending information that is gathering from the computer to the CNC. It's going to download more malware. It's going to break into another process related to the malware that it was just downloaded, and it also started creating temporary files. So this is all the information that's gathering: the name of the equipment, the username, the operating system version, the different user processes in execution. Here we can see all references to HTTP connections that's going to do, and the URL hard-coded. I mean, this is like that because they don't expect that someone is going to be able to find this information out. Finally, we have the drop and execution. This is going to launch a post request, and with the response, and the malware is going to be able to download this temporal path, and then I'm going to be able to invoke a create process after dropping the files downloaded. So let's analyze case by case. We have the first case, which is what we've seen in the presentation at the beginning. So it's a DLL of 64 bits. This is the algorithm that we could see. We have the key, we have the vector, which comes from the data sections, like the key. This is going to do an XOR operation in an array operation. Then I'm going to shift the result with some bits, and then I'm going to apply another operation with the key. Another XOR operation with a key. Everything that I explained before can be applied to this case, but I just want to mention that the contact URL is like that, maliciousURL.com/export. Computer name, username, operating system, peer, user process, etc. Then case number 2, instead of being an URL of 64 bits, it's 32. And instead of having all the coding written as an spaghetti coding without any order, it's now organized per function so that it can be reused. So this is an example of the decompression function, which is segmented and simplified. As we can see, this takes place in different stages. The for loops is still there. We have the decompression function here, which now it looks like that. It can be expressed as a left shift or 4 bits of the array that we've mentioned before. This suffers an XOR operation plus an offset which has been hard-coded. Then the unpacking is exactly the same, but they've added another packaging layer, and UPX. UPX is the most well-known packer, the packer that everybody knows, and the most simple one. And the unpacking was well done because we could see that once that we could unpack the malicious DLL2 in a correct way with the same tool. As for cases number 3 and number 4, they are very interesting too. They are similar to the previous cases. In fact, case 3 is similar to case 1 and case 4 is similar to case 2. Characteristics are the same level of the obfuscation, etc. The difference is that the DLL injected is different. It's changed drastically. And what happened in this new DLL? Well, it's still obtaining profiling information, but now it can skip the process from the exit point, and it remains with the last process identifier. And why that? Because that way it can control other processes. So it's going to obtain the process token of the victim process, and then it's going to do a lookup privilege value in order to obtain the LUID, which is the permit structures that shapes my architecture in order to access other processes. So this allows you to access other processes as if you were the local admin. And finally, it enables these privileges with adjust token privileges, and it can get my own the process identification and the structure of permits that I can get. Once I can access the memory and once I can do operations that before I couldn't do, I'm going to do a reflective load again. Have a double reflective load. So in the first place, well, this reflective load, of course, is invoked because as a parameter I've downloaded the file, and I will try to download reflectively the second malware that I've downloaded. So the reflective loader is obtained through RVA. Then it saves memory in foreign processes with virtual alloc X and starts writing with write process memory. What is it going to try to write? It's going to send a variable to remote thread. It's going to wait until it has a virtual alloc in order to store the response or other type of event that may arise as a response to the thread. And finally, we're going to have the malicious DLL. And here we have the create remote thread, which is passing the alloc-based export in order to also obtain the reflective loader address. What am I doing with this remote thread? I'm invoking that malicious process in order to continue with this reflective loading. In case this malware is not going to be able to do that, it's going to break into a process, and it is going to do a reboot of the machine. Case number 5 is more like an anecdote. They changed the initial code, and in fact the IDA was not able to show it as a normal code. In fact, I had to start analysis with the debugger directly in order to reach stable coding areas. Here we can see jams, conditional jams, in which some calculations are being done, dynamic jumps, hard-coded jumps, etc. When I've already analyzed a lot of samples related to that, and when I consider that I'm in a stable coding area and that I can recognize that area, I have two options. Either I keep what I have, or I drop that and I throw it to the IDA in order to see what happens. In fact, this code is quite similar to the code at the beginning of the presentation. It seems to fake to be a legitimate string. We see the virtual alloc and we see the loop with the obfuscation. We can see that this is a DLL of 64 bits because the deobfuscation code is the same we've seen before. And all the obfuscation codes of 64 bits are going to be specific of that. And now comparison and evolution. What's the look of that in a graph, in a diagram? So we have a main project in which we start organizing two cases, case 1, case 2, 64 and 86 and 32 bits. We see the double packaging, sorry, 82 and 86 and 64 bits, sorry. Then in the second state, chronologically speaking, we see that everything is kept, but the injected DLL has changed, and in the last case, in case number 5, we can observe that the initial wrapper has already changed. Campaign identification. Well, so the attackers behind this campaign were TA505, which is related to the downloader Get2. This theoretically, why I'm saying so? Because sometimes, because of geopolitical issues, some actors try to blame some other actors. So even though my identifiers confirm to me that these are the attackers, I cannot say for sure that these may be some cyber attackers pretending to be TA505. How did I find out that these are the attackers? Well, we have the vector of entry which matches things that I've been researching, such strings, RD64, RD86, also the URLs of the command and control pretending to be Microsoft URLs, help-me-2, and also command and control. After analyzing these and applying JAR rules and consulting public and private feeds in which researchers have been doing some publications, I've been able to extend my knowledge in this and identify these actors and prepare a report in order to explain that we've got the sample and we can act regarding that. Then I would like to show you the MD5s and the URLs in case you want to reverse to confirm that this is true and that all this information matches. Here we have the GitHub of Stephen Fewer, who discovered the reflective DLL injection technique, so no better place to get to know about this than the website of ired.team, in which we can see how this technique could be implemented. This is very interesting because sometimes in the defense part we forget that in order to learn how the malware works, we need to be able to replicate it, because we are going to be able to know all the problems and all of the different cases that we are going to obtain with this malware. And finally, in order to finish my presentation, I just want to show you the Twitter of the researcher is about student. Here you can see a tweet in which he explains the whole campaign of TA505, and this also is going to help you see that all taking into account all the information that we achieved. Probably this campaign was launched by this attacker, this actor. This is it. Thank you very much. Thank you to CyberCamp for having invited me and for promoting cybersecurity. And if you have any questions, you can ask me right now, or I will be also available for you to talk to me after the presentation. Thank you very much.
¿Dudas? ¿Preguntas?
Are there any questions? Any doubts? Okay, well, thank you. Thank you again, and thank you for attending to my presentation. Thank you for being interested. I think that it's very important for young people to participate in this type of events. Otherwise, it couldn't make sense for experts.